Hello, everyone. Welcome to the CanaDAM session, and I have pleasure to introduce Sus Dantamora, who's going to talk us about probabilistic projections.
Thank you for organizing for inviting me. Thank you for everyone for being here. I know that in the schedule is François Bejon, but it's not here. This is not, yeah. So if you came here for him, stick around. Today, but I'm really excited today to talk about this project I've been working on with my supervisor, Oli Amandostam. Um, Today, what I really want you to take from it is to learn what probabilistic bijections are. I want you to learn what they are, what they're for, because I think they're very useful. And in doing so, I'm gonna show you how we use this on non-attacking feelings to prove stuff for McDonald polynomials. But if you happen to not care about McDonald polynomials, which I guess not a lot because people in this room care about McDonald polynomials, then I think you still have something to take from this talk, which is the idea of probabilistic bijections. But before going there, we need to go a little background on McDonald polynomials. Okay, this was working on. Oh, it's the other side. All right. So brief overview. In 88, McDonald defines symmetric McDonald polynomials, which are a unique basis under some triangularity and orthogonality conditions. They extend many polynomials that people care about. For example, Jack polynomials, Hollywood polynomials, Whittaker polynomials, Schur polynomials. And they are polynomials. Oh, that pointer. This is the wrong direction that I think up and down should be. But they have n variables and two extra parameters, q and t. And when you select special cases of q and t, then that's when you get these extensions. Sorry, these is an extension of, and they're indexed by a partition lambda. In 66, McDonald, and also by the same time, some other people kind of simultaneously defined the non-symmetric version, where instead of being indexed by a partition, they're now indexed by a composition alpha. And the idea is that you define this less nice object so that you can prove stuff about the original symmetric function that you have. So they help understand them. And they also extend other things, for example, Demeter characters and atom polynomials. But neither of these two is what I'm actually going to talk today. I'm going to talk today about, up is the other way around, down. I'm going to talk today about permuted based on McDonald polynomials, which they're a generalization of the non-symmetric McDonald polynomials, and now they're indexed by not only a composition, but also a permutation. They can be described as a transformation of non-symmetric McDonald polynomials by Demeter-Ludwig operators, or as eigenfunctions of some version of Chernigg-Dunkel operators. And if you don't know what these means, it's fine. I barely know what they mean. Because what I really care is that they are wagering the functions of non-attacking feelings. So these are really words that if you know what they mean, then you know what they mean and you get what they mean. But all right, so that's all I'm going to talk about in general about McDonald polynomials. And right now, what you need to know is that these version of McDonald polynomials, they are wagering functions of non-attacking feelings. So what are non-attacking feelings? Whenever you hear the word feelings, you should think of a bunch of boxes and you put numbers on them. And so what for me is a bunch of boxes? So my boxes, my diagrams, that's why we call these collection of boxes, they're indexed by composition. So start with the composition alpha, for example, 2, 3, 0, 1, 2, 0. And then we go column by column by putting that number of boxes as if the gravity was turned on and they are all going down. So we call these skyline diagrams because they kind of look like skyline, I guess. And we augmented it by putting another row in the bottom that we call the basement. So these are the augmented skyline diagrams of a composition alpha. And that's a very lengthy title, so I'm just going to call them diagrams of alpha. These red boxes, sometimes they're special and treated differently as the other boxes, but sometimes in other cases, they're treated as kind of the same. In such a diagram, we say that two boxes are attacking if they are in the same row or if they're in consecutive rows and the top one is to the right. Some people take this second definition as the other way around and it's consecutive rows and the top box is to the left. If you are one of those people, bring your mirror and see your talks through the mirror. But it's very annoying because sometimes the same person in different papers uses the different terminologies. And this is even in English notation ish. There are some people who like rotate, and so it's a mess. Anyways, that's what I'm going to use. So they are attacking if they're in the same row or if they're in consecutive rows and the top box is to the right of the bottom box. Now, finally, what is a non-attacking filling? So a filling is basically you put a bunch of numbers in these diagrams. The numbers go from 1 to n, which is the length of your basement, sorry, of your partition, of your composition. And the diagram of alpha is basically you just put a bunch of numbers there such that attacking boxes have different entries. That's the only condition that you need. So here we have an example of a non-attacking filling of shape 2, 2, 0, 1. And because the bottom row, the basement, they're all different because they are all attacking each other, they form a permutation. And we also call that permutation the basement of this filling. So for example, this filling here has shape 2, 2, 0, 1 and basement 3, 1, 2, 4. All right. From such a filling, we can also get its content. So we just count how many of each number appears, excluding in the basement. So for example, this filling has content 1, 2, 0, 2, because there's 1, 1, 2, 2s, 0, 3s, and 2, 4s. And from that, remember that we eventually want to get to polynomials, right? So from there, we can make up polynomial using the x variables by just recording how many of each time these things appear. All right. I'm trying to go very fast because in some sense the details don't matter. What really matters is that whatever I'm doing here is gonna make up to the permuted Bayes and McDonough polynomial. So there are two statistics that we care about these fillings. The first one is the major index, which is computed by going through all boxes such that the box on bottom of it is smaller than it. And then you sum this quantity, which is 1 plus the lag. And the lag is the number of things on top of it. So for example, that first entry 2 has 0 things on top of it. And so it contributes 1 to the major index. The next 4 has 0 things on top of it. So it contributes 1 as well. And the last one has 1 thing on top of it. So it contributes 2. That one here is bigger, is smaller than the thing on bottom, so it doesn't count. And this 4 here is also the same, so it doesn't count. And so that's the major index. It's 4. The other statistics that we care about is the co-inversion number. So there are these things that we call triples, which are these L-shaped things. I'm not going to tell you exactly which ones are triple, but they look like L's. And depending on the relative order of the numbers, we can either call them co-inversion triples and inversion triple or inversion triple. So I'm not going to tell you exactly how they are, but I'm always going to draw the co-inversions in purple and the inversions in orange so that you know which one is which one. So in this case, there are 3 co-inversions, so the co-inversion number is 3. All right. Then the weight of a non-attacking failing is going to be defined as Q is going to count the major index. The T is going to count the co-inversion number. So we computed those before in our example. And then we're going to have this product over all entries that are different from the entry below it of this weird thing. This lag is the thing that you learn, right? The number of things on top of it. And this arm is related, but not exactly the number of things that the box attacks. And so here in this example, there are 4 boxes that are different from the box below. So that's why you see that there's a power of 4 here and there are 4 things in the denominator. All right. From that, we have a generating function formula for the permuted basement non-symmetric McDonough polynomials. So they are the sum overall of the non-attacking fillings with a fixed shape alpha and a fixed basement sigma of that x part is going to take care of the content and this weight that we just defined. And I'm going to take a second so that I can stare. I'm going to drink water. All right. Why do we care about that? Why do I care about that? Well, in 2019, Alex Anderson was studying the symmetries of these exact objects. And one of his results involves this permuted basement McDonough polynomial indexed by partition lambda and permutation sigma. That is the shortest permutation that sends lambda to one of its rearrangements alpha. Well, in 2022, Cortell, Mandelstam, and Williams studied the asymmetric simple exclusion process, which is a model of interacting particles, and has to do with physics and etc., multi-line queues. And one of their results involves kind of the same thing, but where the permutation now is the longest one that sends lambda to alpha. And when my supervisor first told me about this, we were under the impression that these were the same. And if you're looking through your mirror to this talk, your mirror should be magical and change the word shortest and longest to the opposites, right? Because in the mirror, they're different. So we took a long time to discover if they were actually talking about different things or if they were one was talking through the mirror with the other person. But no, they were actually talking about different permutations. However, when we put things on stage, they gave the same polynomials. And so we tried to string all the theorems together. We couldn't really prove them. So that's one of the things we proved. We proved that these two polynomials are the same, and there's nothing really special with shortest and longest. It's just anything that does this. And so there's a more general version of this theorem, which is basically if you have a composition and two adjacent parts are the same, then you can swap the basement, the entries I and I plus 1 in the basement. Come on, let's just stare a little bit. Yeah, so that's the main result, and that's what I'm gonna use the rest of the talk about to prove that E alpha sigma equals E alpha sigma Si, which is the version of sigma where you swap the entries I and I plus 1, in the case where alpha I equals alpha I plus 1. How do we prove this? The way that we do is, which I think is very nice, we construct this probabilistic bijection between the things that generate this and the things that generate this. All right. If you got lost, it's fine, because now I'm going to talk about probabilistic bijections, and I think that's a really interesting thing. So let's just generalize a little bit of our goal, right? So our goal really is that we have two weight-generating functions, and we want to combinatorially prove that they are the same. And if you've taken a class on that recently, like I did, you have a strategy, which is try to construct a weight-preserving bijection between these two sets. So let's just recall what that is so that we have that perfectly. So a weight-preserving bijection first is a bijection. So it is a map that has an inverse map. And whenever you map some element S to some element T, you want the weights to be the same. And you like weight-preserving bijections because if there exists a weight-preserving bijection between two combinatorial sets, then their generating functions are the same. All right, that's all and good, but what if you can't? What if it's hard to find one, or maybe even impossible? Then I guess you can know the answer, and the answer is probabilistic bijections. So now probabilistic bijection is going to be a pair of maps to an algebra, and here the algebra is just, you should think as them as the real numbers, but they don't really need to be the real numbers. So it's a pair of maps that tells you, like, if you give something in S and something in T, is going to tell you the probability that that thing in S is going to get mapped to that thing in T, and you have a reverse map that goes the other way around. And the things you want these two maps to satisfy is, first, you want to explain why we call them probabilities, and the only reason we call them probabilistic is because the probability sum to 1. So if you fix some element S and you sum all the probabilities going out of it, it sums to 1, and the same thing on the other side. And the second condition that we need to have is this thing called balance condition. So you want the weight of some element in S times the probability that that element in S gets mapped to some element in T equals the weight of T times the probability that you get mapped back. And I just want to iterate that if the probabilities are all 0 and 1, so it's like a deterministic case, then we return to weight preserving bijection, right? Because these conditions going to become the weight are the same when both numbers are 1. So this is really a generalization of weight preserving bijections. And the real nice thing is that this still has that proposition that we had before, right? So if there exists a probabilistic bijection between two combinatorial sets, then their weight generating functions are the same. And it's really easy. I'm going to prove them real quick. So you take this first thing, you sneakily put a 1 here. Then you use the fact that all the probability sums to 1 to expand this 1 as that thing. And then you use the balance condition to swap all of the S's and T's here. And then you go back. So it's really not a deep statement. But it's really nice. And here's for example, and it's spoilers, that's what we're gonna do. So here we have three fillings, and here we have two fillings. We could never ever dream of finding a weight preserving bijection between them because you can find a bijection. There's three and there are two, so there's not even a bijection. But here, so the number here on this side are the weights of these fillings. But here I'm drawing to you a pair of maps, and then you can go and you check that every pair of maps the balance condition holds, and then you can check from every filling the sum is 1. And then doing these local checks, you can get the global conclusion that the sum of these three things equals the sum of these two things. So that's the kind of thing that probabilistic bijections let you do. All right. Now in these last minutes, I'm gonna actually go through this probabilistic bijection that we made. So let's recall our goal, right? So our goal is to construct a probabilistic bijection between these two sets. So they have the same shape, but the basement differs by this transposition. And we know that the heights at column I and column I plus 1 are the same. So the naive idea that you might have is you just take the two entries in the basement and then use the swap. But a problem that could happen is that, like, if B equals D here, it's not a problem. But here's a problem because they're attacking. So one idea for a fix is if you get a problem in the next row, then you if I swap A and B here and I get a problem, then I'm also gonna swap C and D to try to fix that problem. But then you could get a problem the row above of it, and so you do that kind of recursively. And there's just a refinement that I'm not really going to depth because we have the weights, right? And so to take care of the weights, the probabilities also help with taking care of the weights. And so at some step, we're not necessarily going to deterministically swap or not, and we're going to probabilistic swap or not. Let's go through it in an example. So let's say you have this alpha, you have this sigma, and you have this input. Here my I equals 2, meaning that I want to swap this 1 and this 3 here. And the algorithm that we have, it doesn't change any entries that are not in these two columns. So I'm not even going to draw them in the next slide. So here are them. What we do is we look at this 2 by 2 here. So in this case, they're all different. So we see if we were to swap, what would happen to the co-inversion number. And here the inversion types change. And so what we do is, sorry, I should have mentioned, this finger here means that I really want to swap 1 and 3. So this is to remind me that I want to swap 1 and 3. So I try to swap it, right? And here the co-inversion, the inversion type changes. And so what I do is I still swap because that finger tells me that I need to swap. But I move the finger up, meaning that I also want to swap the things on top of it. So in this case, this happens with probability 1. Now in this other case, we have two equal things on the left. And that is one special case that we actually, with some probability, we do swap the 2 and 4, but then we remove the hand, and then we just call it a day. That's one of our outputs. And the probability depends on these entries and on the shape. And with the complementary probability, we still swap because that finger tells us we need to swap, but we also move the finger up. And now in this case, we have this diagonal position. And so what we do is we just swap and then we call it a day. And so with some probability, we swap the first two rows, and with some other probability, we swap the first 3 rows. And that's kind of the kind of thing that this looks like. Here are all the rules. So actually, that middle rule that we split is the only rule that we actually have probabilities. All of the other rules are deterministic. And all they do is you swap the thing that the finger is pointing, and you either delete the pointer and then you call it a day, or you move the pointer up. And the magic is that this describes a probabilistic bijection between these two combinatorial sets. Right. So just an overview. Probabilistic bijections, they generalize the weight preserving bijections. They're very nice. by writing the permuted-based McDonald polynomials as a draining function over these things called non-attacking fillings, and constructing this probabilistic bijection between the non-attacking fillings x by alpha, sigma, and alpha in the swap version of sigma, then you conclude that this permuted-based McDonald polynomial equals this permuted-based McDonald polynomials via combinatorial arguments. And that's it. Thank you very much.